Good afternoon, and welcome to Practical Web Cache Poisoning. Have you ever been working away and just noticed something that wasn't quite right and thought, that's strange, but that's rather complex. I think I'll just deal with that later on, when I have more free time. For years, web cache poisoning has been a vulnerability that people didn't want to think about. It's existed mostly as one of these theoretical vulnerabilities that are more often used to scare people than actually proven to exist. And for years, I lived in fear of web cache poisoning and its notorious complexity, but I recently found myself in a situation where I had no choice but to try it and discovered that actually, web cache poisoning is wonderful. So today, in this session, I'm going to share with you practical tools and techniques to detect, explore, and exploit web cache poisoning. I don't normally share the story of how I got started on research because it's generally pretty dry, but this one time I'm going to make an exception. I started out about a year ago with a simple plan and a lot of optimism. I wrote this tool to find hidden query parameters called ParamMiner, and my plan was I was going to run this tool on lots of sites. It would find some really cool, weird parameters. I'd find some awesome bugs in those, and I'd give a talk about that. And it started off quite well. I found some quite remarkable query parameters, like this one here. But the next step just went horribly wrong. The most interesting thing I could find in these query parameters that was actually serious over and over was boring old reflected cross-site scripting, which is not something that I really want to give a talk about. And so I thought, okay, well, this hasn't worked out, but maybe all the cool vulnerabilities are actually hiding in cookies. So I hacked up my code to guess cookie names as well, set it running, and found something that looked super promising. And about 8 hours later, I got absolutely nowhere and had to admit, actually, that was a waste of time as well. And at this stage, I only really had one option left, which was to once again hack up the code and this time make it guess HTTP headers. So I did this, and I set out guessing headers and found loads of weird and wonderful headers. And yet, once again, in these headers, I found nothing but cross-site scripting, which I was pretty sick of at this point. And cross-site scripting in headers is even less interesting than normal reflected XSS because there's no way for me to make someone else's browser send a header across domain. There was only one tiny glimmer of hope, which was that some of these servers that had XSS in their headers used caching, and just maybe I could use their caches as an exploit delivery mechanism for my header-based XSS. So I tried this as an absolute last resort, and quite surprisingly, it actually worked. So first, I'm going to talk about what cache poisoning is and how you can find it. Then I'll demonstrate cache poisoning on a bunch of well-known websites and show what goes wrong and what goes well. And then I'll also do a live demo on a very well-known piece of software and talk about how not to get your cache poisoned. And then finally wrap up and take 5 minutes of questions. So, first of all, a bit of context as to this presentation. In this presentation, I'm not going to be talking about browser cache poisoning. Browsers have built-in caches. These are client-side caches. And from a security point of view, from a cache poisoning point of view, they're not that interesting. So I'm not talking about those. I'm talking about server-side caches. Also, web cache poisoning is not web cache deception. Web cache deception is a really cool technique that was there was a Black Hat presentation on it last year, and it's about tricking caches into storing sensitive information belonging to users so that the attacker can get access to it. Web cache poisoning is about using caches to save malicious payloads so those payloads get served up to other users. So it's kind of related but the inverse, and the way you exploit them and find them is completely different. Also, this is not about web cache poisoning using response splitting or request smuggling. These are both cool techniques that will get you cache poisoning in the right circumstances, but a lot of the time they don't really work and they're not the topic of this presentation. Finally, and most importantly, practical web cache poisoning is not theoretical. Every example I'm using in this entire presentation is based on a real system that I've proven can be exploited using this technique. So first, let's take a very quick look at how caching is supposed to work. Here, we've got 3 users fetching the same resource one after the other. This resource might be an image or a JavaScript file or even just a HTML web page. And when the cache sees this resource being fetched for the first time, it saves a local copy of it, which means it can then serve that copy up to other users without having to communicate with the backend server, which speeds the website up and everyone's happy. Our objective with web cache poisoning is to send a request to the server that causes a harmful, malicious response to come back to me, and then we want the cache to save that and serve it up to other users. The first step to achieving this is to ask the question, how does the cache know that those first 3 users are all fetching the same resource? It can't be doing a full-on byte-by-byte comparison on their HTTP requests, because HTTP requests are full of all kinds of junk. For example, if those users had different web browsers, the user agent header would be different, so the caching wouldn't really work. Cachers address this problem with the concept of cache keys. They say, we only care about certain parts of the request, generally just the host header and the request line. So this is all that the cache does a comparison of to work out if 2 requests are accessing the same resource. And that's all well and good, but it leads us on to the next question, which is, well, what happens if there's something important and it's not included in the cache key? This is where things start to get interesting. So here we have 2 requests to the same website, to the same URL, to retrieve a white paper, but one of them is trying to fetch it in English and the other one is trying to fetch it in Spanish, thanks to this language cookie. And that's absolutely fine, and that will work just great until you put a cache in front of this website. Once you do that, it will break because the cookie header is not part of the default cache key, and so the cache is completely oblivious to this language cookie. And that means that if the English user were to fetch this white paper first, they would accidentally poison the cache with the English version of the white paper, and all the users of other languages would end up receiving the white paper in English. And by itself, well, obviously that's just a harmless nuisance. But this is the behavior that we're going to turn to our advantage. In effect, everything that's not part of the cache key is part of the cache poisoning attack surface. So how do you find cache poisoning? Well, the first step is to identify an unkeyed input. So probably a HTTP header or a cookie. And I'm releasing the tool Param Miner as an open source tool that works in the pro and free versions of Burp. So everyone can just run that tool, and that will hopefully do a decent job of finding some unkeyed inputs on your site. Once you've found the input, the next step is to work out if you can do anything interesting with it. If genuinely all you can do with this input is change the language, like in the example I just showed you, well, that's pretty boring, right? That's not really worth following up on. But a lot of inputs can be used for more interesting stuff. While you're doing these 2 steps, it's absolutely crucial to specify a random cache buster, a parameter that changes its value on every request. If you don't do this, then you risk getting a response from the cache rather than from the backend server. And that will effectively make any unkeyed inputs that you're sending completely invisible. I think that this is why cache poisoning has remained so low profile for so many years, even though once you know how to do it, it's actually pretty easy. Once you found your unkeyed input and established it has some kind of exploit potential, the next step is just to try and get it saved in the cache. And you may find that's already happened, because it's kind of the job of caches to save stuff, so they can be quite aggressive about it. But if your response hasn't been saved in the cache, then you'll need to fingerprint the cache rules, because they may be saying things like, we're only going to cache responses with certain file extensions or certain status codes and so on. And then you'll just need to trawl the app to find the target page to find a page that fulfills the conditions that you can poison. During this step, it's important to have a static safety parameter. I'm going to talk more about that shortly. And that is pretty much all the theory of cache poisoning. So let's take a look at what happens when we apply this methodology to some real websites. Now, part of the goal of the section is just that I want to show you that cache poisoning does work on real sites, but I've chosen these specific examples to show you some of the challenges you may run into with cache poisoning and give you some ideas as to how to deal with those challenges. As usual, I've only targeted sites that have bug bounty programs, and all the specific examples I'm showing you here have been fixed, but the techniques still work on many other websites. I've exploited targets with all of the caches that you can see logos of here, and ultimately I think basically all caches can potentially be poisoned using this technique, because it's a design flaw in caches rather than an exploit for a specific caching system. So to begin, we're going to take a look at the homepage of Red Hat, popular Linux distribution. Now, if you look at the homepage, you might think this doesn't look very promising, because we've got this cache control no cache header that explicitly says don't cache this. And also, there's no other headers that suggest that this site is actually using caching. So it would be tempting to give up at this point, but that would be a mistake because headers will lie to you. So if you run param miner on this and tell it to guess headers, it will quickly find that the X-forwarded host header is reflected inside a particular piece of HTML. And so that's our unkeyed input, right? And the next step is just to see, well, what damage can we do with this? Now, what do you think the most obvious attack to try here is? It's cross-site scripting, right? And sure enough, we can break out of that input and inject arbitrary JavaScript into the response. Now, by itself, this is useless, right? Because we're only exploiting ourselves. We are 100% relying on their cache to deliver this exploit to genuine users. So we need to see if this is being saved in the cache. And to do that, we just send the same request, but we don't send any funny headers. So we're just doing what a normal user would do. And then we look at the response, and sure enough, our malicious JavaScript has come back. So that was it. We just got full control over the homepage of redhat.com. And it wasn't very difficult, right? The only other point that I should make is this safe equals 1 parameter that's highlighted in blue. That's not part of Red Hat's website. That's something I've manually specified, because if I didn't do that, there was a risk that a lot of genuine visitors to Red Hat's site would start seeing pop-ups, and they might get a bit upset. So headers will lie to you, but they will also tell you useful things. So having just mentioned that safety parameter, let's pretend you're a malicious person and you genuinely want to poison the actual homepage of the site. This is slightly more difficult because this means you're in a kind of a race with all the genuine users of the website, because you want your malicious response to be cached rather than a normal innocent response. So you need your request to be the first request to hit the server after the cache entry expires. And sometimes headers will really help you out when you're trying to achieve that. So this is the homepage of Unity3D.com, makers of a well-known computer game engine. And we can inject JavaScript and stuff with this X-host header. But the interesting thing is, these age and max age headers, taken together, specify the exact second that this response is going to expire in the cache. So that tells us the exact second that we need to start spamming our payload to the server in order to take full control over the site. HTTP headers can give you other clues too. So here we've got a different website, which unfortunately I can't name, but it is quite well known. And once again, we can inject JavaScript using the X-forwarded host header. I think there's something in Rails that just adds support for this header by default. So if you're using Rails, you might want to check that out. But the interesting thing here is this vary user agent header. So that's an instruction to the cache to add the user agent into the cache key. So that means that this request I've sent here will poison the cache, but it will only poison it for other people using the same web browser as me. And that's both a blessing and a curse. It's a bit of a headache because if I want to poison the majority of visitors, then I need to send this request over and over with every possible user agent. But on the other hand, it gives me the chance to be a bit more creative and selective about who I target. For example, perhaps I happen to know that the development team for this website always uses Microsoft Edge. Well, that means I can poison the cache for everyone who's not using Edge. And then the developers are going to have a really hard time figuring out why all of their users keep getting exploited. Okay, so I've looked at 3 websites, and in each case, the poisoning has been done using basic reflected cross-site scripting. Although through the cache poisoning, we've escalated it to stored XSS. So it's still serious, but it's not always that easy. On this website, catalog.data.gov, the X-forwarded host header is reflected inside this data site root attribute. And they're encoding this input, so we can't just break out and inject HTML. To exploit this, we need to figure out what this attribute is actually for. So to do that, I set up a header injection rule in Burp, so it would just add this X-forwarded host header to all of my traffic. And then I just browse the site. And what I found was when I loaded certain pages, my browser sent a request to the collaborator server to fetch some internationalization data from it. So using this unkeyed input with cache poisoning, we can make people visiting this website fetch some kind of internationalization data from our website. Let's have a look at what this data is supposed to look like. It's meant to be a mapping of English phrases into the phrase in a different language. And the translated phrase is just concatenated into the DOM. So what we can do is tell everybody, use our translation file. And then we can make our own custom translation file that translates English phrases into malicious HTML that exploits users. So the end result of this is that if anyone views a page on that website that has the text "show more" on it, then my exploit fires. And this is this thing where you serve up malicious JSON by tricking the site into requesting JSON from your website is a really common pattern with cache poisoning. Now, after that exploit, I forgot to delete the header injection match and replace rule in Burp. And a few days later, when I was just tidying stuff up and closing everything down, I noticed a really weird request had hit the collaborator server. So the null origin is quite rare by itself, but at this point, I'd never seen a lowercase origin header coming from a browser before. And it definitely didn't look like this request had come from data.gov. And investigating, it turned out that it came from a core Firefox feature called Mozilla Shield. So this is a system for silently installing extensions in the background for research and marketing purposes. It's turned on by default in Firefox, and you may have actually heard of it because they hit the news last year when they installed a Mr. Robot extension on a lot of systems, and it was meant to be invisible when it wasn't, and some people got upset. So when you open Firefox, it sends this request, which is to fetch a list of URLs that contain recipes, and the recipes specify what extensions should be installed. And it also resends this request like every 30 minutes or something like that. But that's fine, but of course for me, Burp had injected this header, X-forwarded host, and that had overridden the URLs in the response. And they were using caching and that header wasn't in the cache key. So the end effect was I could make every Firefox browser on the planet connect to my system to fetch this list of recipes which specify what extensions to install. So that's pretty cool. That's like 15 million browsers or something like that, right? So that raises the question, well, okay, what can you do with these recipes? Now, unfortunately for me, Mozilla was smart enough to sign these recipes. So I couldn't just make my own malicious extension and then install that on 50 million computers. But what I could do was replay old recipes. So for a start, I could reinstall the Mr. Robot extension on everyone, which would have been hilarious. But more practically speaking, I could look through all the extensions that had ever been supported by the system, find one with a known vulnerability, and then basically forcibly inflict that vulnerability on every copy of Firefox worldwide. Also, there were some unsigned versions of these recipes, which aren't used by Firefox, but they are apparently used by Mozilla's back-end recipe development infrastructure. So I could potentially have used that to gain access to that infrastructure, got hold of the signing key, and then got my 50 million browser botnet. They patched this one remarkably fast when I reported it. So a reoccurring theme in cache poisoning is that we'll find some kind of unkeyed input, and at first glance, it will look completely useless, like this. X-forwarded host header on this website of a well-known computer game that I can't name. This value is reflected in the domain attribute of the set cookie header. Now, as far as I know, that's more or less useless. Also on this website, the X-forwarded scheme header, if you set that value to anything other than HTTPS, the server responds with a redirect to itself. Once again, harmless. But if you send both of these headers at the same time, then suddenly we've got a redirect to a website of our choice. And because this is being done at the server level and they've got the caching set up right, I can effectively replace any response on the entire server, any URL on the whole site, with a redirect to my site. So using that, I could redirect post requests to steal CSRF tokens, and I could also redirect JSON fetches in order to serve up malicious JSON and once again get DOM-based cross-site scripting on various pages, much like what I did earlier on data.gov. Now, some systems go beyond using headers to generate URLs, and they use it for internal routing, which is really pretty cool. So goodhire.com is hosted using HubSpot, and HubSpot appear to use the X-forwarded server header to work out which client you are. Now, we can't exploit this directly because they're encoding the input. To exploit this, I needed to register myself on goodhire.com, make my own website, put some malicious HTML on that, which they let me because it's my own website, and then trick Goodhire into serving that up, and trick HubSpot into serving that up on goodhire.com. So using this, and then of course Cloudflare would cache that and serve that up to everybody accessing Goodhire. So using this, I could take full control over any page on any website hosted on HubSpot. Now, I reported this to Goodhire because those were the guys with the bug bounty program, and they passed it on to HubSpot, who decided to resolve the issue by permanently banning my IP address, which wasn't very polite. But I've checked back, and it does look like they have fixed the root issue. So if you're using HubSpot, then I think you're probably okay. Right, now this one is my second favorite attack in this research, partly because I'm exploiting a security company because they use their own security product on their website. So blog.cloudflare.com is hosted using Ghost. And Ghost is doing something with the X-forwarded host header. But if we try the attack that just worked on HubSpot and specify our own domain name after signing up with Ghost, it doesn't work. They give the correct response after a mysterious 10-second wait, which I never figured out the cause of. To exploit this site, we need to kind of hit a different point in Ghost stack. And we can do that by, instead of specifying our custom Ghost domain name, we can specify our Ghost subdomain, which triggers a redirect to our custom domain. So using this, I could replace any response on that site with a redirect to my domain. However, when it came to getting this stored in the cache, things got a bit tricky because Cloudflare's site was configured to only cache things with certain file extensions. So I could redirect images, which was kind of funny. I could just hijack any images on any of their blog posts. But when I tried to do something useful with it and hijack JavaScript, I ran into quite a significant problem, which is that this redirect the Ghost was issuing was using the HTTP protocol rather than HTTPS. And that means that browser's mixed content protection kicks in and blocks this redirect, effectively completely preventing my attack from working. Now, I spent ages trying to find a way around this. And I was even considering just contacting Ghost support and just asking them to change the redirect to HTTPS. But there were obviously some minor ethicals with that plan, so I didn't go ahead with that in the end. What I decided to do instead was to try and crowdsource a solution. So I built a replica of this mixed content problem, and I stuck it in my online hacking game. And then I tweeted saying, here's a challenge, there's no known solution, and the first person to solve it will get half the bug bounty. And that led to a great community response and 2 solid solutions. The first one was someone found that in Safari, if the website you're redirecting to is in Safari's strict transport security cache, then it will get automatically upgraded to HTTPS before the mixed content protection block happens. So that means I can exploit Safari users. Also, someone then found in Microsoft Edge, if your response sent over HTTP is a 302 redirect to a HTTPS URL, Edge will just follow that and execute it, which is great for me. So that means this exploit will work on Edge users as well, and it's also a full mixed content bypass for Edge. So if there's any Microsoft people in the audience, you might want to look at that one. So using this, the end result is if you went to blog.cloudflare.com or any other website hosted on ghost.org, I could take full control over the site, over your account on there if you were using Edge or Safari. And if not, well, I could still hijack images, which would be useful for tracking purposes at least. Right, now things are beginning to get more difficult. So here, using this exported host header yet again, we can take control over this open graph URL meta property. We can't break out and get XSS, so we need to figure out what this property is for. Open graph is a protocol by Facebook for specifying what happens when your website is shared. So if someone presses the share button on your page, or if someone just shares your URL on Facebook. And so using this value that we can control, we can effectively make someone share arbitrary content when they try to share this web page. Now, to get this cached, I had to find a specific page on the site that had the right caching headers. And I also had to specify this session ID cookie for some reason. But even after doing all of that, my like hijacking attack wasn't working. And it turned out that this target was using Cloudflare, and they have a lot of caches. And Facebook was hitting a different cache from the one that I was poisoning. So Facebook was hitting a cache that was in Atlanta. So I Googled for cheap VPN servers in Atlanta, found one, and then used that to do the poisoning. And that successfully poisoned the cache that Facebook was hitting. So here's a quick demo. I've had to redact it quite heavily, unfortunately. So on this web page, well-known computer game, someone presses share, and they end up sharing my content. Something particularly cool about this is that Facebook have their own cache. So that malicious Open Graph URL will get cached in Facebook's cache as well as Cloudflare's cache. And that means that even if they fix the vulnerability and then clear the Cloudflare cache, they will still continue to have their likes hijacked until Facebook's cache expires as well. So it's quite a persistent kind of attack. So that was great, but do we really need to hire a VPS every single time that we want to poison a specific cache? Well, I decided to just do a bit of research to find out. So Cloudflare has a lot of caches, you can see them all here, and they have this fantastic feature, which is on any Cloudflare website, you can send a request to cdn/cgi/trace, and you'll get some metadata back. And included in that metadata is the highlighted line, which tells you which cache your request has hit. So I wrote a little bash one-liner that sends a request to my target website, to this trace page, and it routes this request through every single IP that Cloudflare own. And then it looks at which cache this request hits. So the end result is that gave me a list of which IP I could send my request to poison which cache. So generally speaking, you can poison a cache in an arbitrary location worldwide without using a VPS, as long as you're willing to do a bit of recon. Now, at this stage, we've seen quite a few different attacks. Almost all of them have been doing some kind of host override, just because that header is widely supported by a lot of frameworks. I'd also found exploit using some weird one-off headers like bucket, translate, and path_info. And I found one amazing one last week that hasn't been patched yet. But they had a web application firewall that was scanning all the request headers for burpcollaborator.net. So you could specify an arbitrary request header, put burpcollaborator.net in it, and the WAF would block this request, and then that would get saved in the cache. So you could effectively make the WAF think that every single visitor to any page on the website was a hacker and just block them. Anyway, what I want to introduce you to is my favorite header, which is the X original URL header. It also has a companion, which is X rewrite URL, which is supported on the same systems and does exactly the same thing. This header overrides the path that's used by the server. So even before we get into cache poisoning, it's really quite useful because, for example, on Unity's website, they're my favorite example, if we access /admin, they've got a front-end server that blocks that. But if you put /admin in the X original URL, their front-end server doesn't see this header and lets it through. Now, the reason this header is so awesome is because it's supported by an unbelievable number of systems. I originally spotted this header on some targets that were running Drupal 8. And when I reported it to Drupal, the developer was like, "What is this header? I've never seen this before, and I can't find any references to it in our code base." And it turns out Drupal 8 is partly built on Symfony, and Symfony has this header in it. But the only reason that the Symfony framework has this header is because it comes from Zend. So I think in effect, if you're using any framework that's built on a framework that's using Zend, you end up supporting this header. So let's have a look at what we can do with it. Here, so if the target is using an external cache, like Cloudflare, like every example I've shown you so far, then we can replace any path on the server with the response to any other path. So, for example, on store.unity.com, we can't do anything with the query because the query in that header is ignored. But we can swap the paths around. So the effect of sending this request to their server is if someone tries to fetch the Unity for Education page, they get the Unity for Gambling page, which looks like this. So that's definitely entertaining, and obviously there's more harmful things we can do with this, right? Like we can swap the change password page for the logout page, so you can't change your password. But to really prove how dangerous this header is, I need a case study. And for the case study, I'm going to use a vanilla installation of Drupal 8. So Drupal 8 also has an internal cache, which is enabled by default. And this cache is aware of the X original URL header. So we shouldn't be able to do internal cache poisoning with this header, right? But when my colleague Gareth Hayes was helping me out testing one of these sites, he noticed something wasn't quite right. and eventually figured out that Drupal's internal cache has a bug in how it handles this X original URL header, probably because they don't know that the header exists. So this cache thinks that the query string in this header is used. So what we've got is kind of the inverse of what I just showed you. So now we're doing cache poisoning on a Drupal site that does not have an external cache. We can't do anything with the path, but we can effectively replace the response to any query string with the response to any other query. So the end result of sending this is if someone does a search for kittens, they get search results for snuff. And that's obviously, that example is not that great, but this is really quite powerful by itself. But for generic mass exploitation of Drupal sites, we need one more ingredient. And luckily, Drupal provides. So Drupal has this feature on any response that's a redirect. If you specify a parameter called destination, you can override the destination of the redirect. And they do some filtering and stuff to try and make sure this isn't redirecting you to an external site, but we can bypass that fairly easily. So by itself, this is just an open redirect, right? It's nothing. But now we've got all the ingredients that we need to really have some fun. So business.pinterest.com uses Drupal. And on certain pages, they import JavaScript files via redirects. So what we can do is we can use internal cache poisoning to change the parameters on this JavaScript import. And using the ability to change parameters, we're going to inject the destination parameter. And the end result is that when someone loads any of these pages on business.pinterest.com, these pages that are meant to be completely static, they end up importing JavaScript from my website, and I get full control over their account. So that's pretty cool, but that's still not full-on exploitation of all Drupal sites, because we're using this, we can only hijack existing redirects. What we really want to do is hijack arbitrary responses from the server. Now, in every example that I've shown you so far, we've poisoned the cache in order to exploit the end user, the victim. But Drupal is generally used with two caches. You've got this internal cache that's turned on by default, and then every example of it that I've seen in the wild has also had another cache like Varnish, because if you don't have something like that, then it's incredibly slow. So what if the victim of the first cache poisoning attack is the other cache? We can do a kind of two-stage attack. So the first stage is roughly similar to what I just showed you on business.pinterest. We're going to poison an arbitrary redirect response in the internal Drupal cache. But then we can send another request, which will effectively use the poisoned internal cache to move this poison to an arbitrary location in the external cache. And the end result of that is that we can replace any response on the server with a redirect to our site, which is really quite powerful. Browsers weren't built with that kind of attack in mind. And for example, on store.unity.com, you can try and download the Unity installer. But using this cache poisoning, you could redirect the download. So they would be on unity.com, they click the download button, they're still on unity.com, but the installer actually came from my website, and it's malware. And you can use this kind of technique on any Drupal 8 site. So let's try and do a quick demo of this, which is hopefully going to work. So this is just a vanilla installation of Drupal 8. The only configuration I've done is I've turned on caching, and I've put a Varnish cache in front of it. So first, let me just quickly show, if you right-click and tell ParamMiner to guess headers, then that will find some headers, hopefully. And also, as of about now, there's an update to Burp, so the active scan will also find this stuff. Let's see, okay. Well, the active scan worked anyway. So here we can see that that's spotted that, and ParamMiner will probably find the headers eventually, but it's trying millions and millions of headers, so it does take a while sometimes. So let's try and do this attack on it. The first thing you need to do is just find a redirect. So we have one right here. And then we're just going to take that path, and we're going to hit it using the X original URL header and add this destination. So now we're trying to poison the internal cache. And that seems to be working, and we've poisoned that URL on the internal cache. And so what we're going to do now is try and shift this poison into the external cache. So we're going to leave this header exactly the same, but change the path. So we should get the same response, hopefully. Yes, great. So now the cache at that point should be poisoned in Varnish. So now we're going to resend this request as a normal user would, and it looks like it is poisoned. So now if I just go to this website and press the login button, then with a bit of luck, yeah, we end up on my hostile website, which just has a replica of the login page, eagerly waiting for your credentials. So there was a coordinated security release by Symfony, Drupal, and Zend last week to fix this issue. It was super low profile, so please install that if you haven't. Also, there's probably loads of other frameworks based on Zend that won't backport this fix for years, so it's definitely still something that you want to watch out for. And I'd like to give a brief shout out to the Unity security team for letting me use them in tons of examples here, which they didn't have to because it's a private bug bounty program. Okay, defense. The best defense against cache poisoning is obviously not to use caching. That might sound like unrealistic advice, but I think some people, they might do something like, I'm experiencing a DDoS, I'm going to sign up for Cloudflare. And they don't actually particularly need Cloudflare's caching, but it's turned on by default. So they end up vulnerable to cache poisoning. So just turn it off if you don't need it. Regardless of whether you're intentionally using caching though, some of your visitors may be going through servers that are doing caching. So everyone should avoid unkeyed input. Avoid taking input from HTTP headers and cookies as much as possible. And also audit your application with Param Miner to see if you can find any unkeyed inputs that your framework has just sneaked in support for. If you find them, the best thing to do is just to disable these. But if that's not an option for some reason, you may be able to configure the caching layer to automatically strip the headers. And as a last resort, well, if you need this header, you can always add it into the cache key, which effectively means that it can't be used for cache poisoning. So you can grab the white paper online. Param Miner is open source. You can grab that too. And also, for the first time this year, I've built an online cache poisoning challenge in my hacking game, so you can have a shot at that to get some practical experience with it without accidentally taking out any websites. So the three key things to take away are that header-based input is inherently dangerous, frameworks can hide lethal functionality, and cache poisoning is not theoretical. I'm going to take 5 minutes of questions now. If you've got any more after that, feel free to come and speak to me at the back or just chuck me an email. Don't forget to follow me on Twitter. Thank you for listening.